So very good afternoon to you. So today we will discuss about, we will start with reprojection. So today we will learn how we will reproject raster. Then next we will continue with how do we mosaic multiple rasters, like we have rasters with, and they are special, they are spatially different location they are available, and we have to create a mosaic from multiple images. Then we will do some local analysis on any raster. Plus, then we will do some proximity analysis, or that is called global analysis. So we will see with this. So let's start with the reprojection. So suppose we have a raster image in some like coordinate system or UTM projection. From that you want to convert it to some other projection system, that we call reprojection. So here I have a sample image of, I have a dam of somewhere in Uttarakhand area, so that is available in. So let us first open that dam file and inspect what projection system it has, and then we will reproject it to a different projection system. So here I have a file that is Alos Pulsar dam. So this is the name of the file. So now suppose if I open, I will call it at old data set, and the reprojected data set we will call it reprojected or virtual data set. So let us, this is my original file. So let's open. We will call it old DS. So same thing like jidal.open. So first we are opening it the file for reading. So with that file gets opened. Now let's inspect what is the projection system available in this. So same thing, old ds dot get projection. Old ds dot get projection returns as the projection system of this particular file. So it says GeoGCS. So the projection system of the file is geographic coordinate system WGS84, and datum, this is the datum, and these are the other details of the projection system. Now let's suppose if you want to convert it to reproject it to the UTM projection. So UTM 44N. So for that, first we need to create our projection system in which we want to reproject our raster. So as explained in my previous lecture, so first thing we need to create a CRS. So CRS is good from that will come from OGR. So OSR dot spatial reference. So that will create a spatial reference system. So once the CRS is created, then actually we are calling it as UTM projection. So there we need to call it like CRS dot set projected CS. So this is, we are going to create a projected, our original projection system is a geographic coordinate system. Now we want to reproject our image to a projected coordinate system. So there is a function in our, once a CRS is created, set projected CS. So what is the name you want to give to your projection? So suppose if you want to give our name, projection name UTM, then actually there are, for some well-defined coordinated, well-defined projected coordinate systems, OSR has some already well-defined predefined method. So suppose your projection system is UTM, so then directly you can call a function set UTM. So you want your projection to be UTM. So actually this name you can give any name, but finally suppose there are certain projection systems which are already defined in this, so that you can call it set UTM, CRS dot set UTM, and you can pass it the number, which number. So UTM has been divided into multiple zones. So UTM 44, and suppose you say that it is north or south, so that also can be defined. So if you say set UTM, if so by default north is equal to 1, suppose if you want to make it as UTM 44 south zone, then you need to pass north equal to 0. So then it will be treated as UTM 44 south. So now we want to create it as UTM 44N. So we have just passed 44, and north by default is 1. Then every projected system will have an associated geographic coordinate system. So again we are calling the other function set well-known GeoGCS. That actually this is WGS84. So with this the projection system gets created. Now suppose if you want to see the details of your projection system, like we can export it to WKT or PROJ4 string, then we can see the parameters associated with this projection system. So if I see the details of this says it is a projected coordinate system UTM, and is based on WGS84 GeoGCS. So now we have created a projection system in which we want to reproject our image. So actually there are two functions available. One, either we can call GDAL.reproject image, or we can call, there is a function called GDAL.autocreate warped VRT. Actually VRT is a virtual raster. So suppose you have an image, multi-band image. Now you have calculated some, you want to calculate some indexes or anything. So you have done some calculation on the image, and instead of completely saving the entire contents of image, what do you want? You want to save only the, you want to save the, you don't want to save the entire description of the image to the disk. So instead of that, whatever calculation you are performing, that just you wanted to save in an image, and rest of things whenever you load the images in memory, so you want that to be done from that create. So that is called virtual raster. So in virtual raster we will describe an XML. So in XML we will describe the description of the file, and instead of writing the entire contents of the file, so when the data will be read relative to the source files. So now what we are doing here, we are creating calling function GDAL.autocreate warped VRT. So this just creates a virtual raster. So virtual raster means it just it's an XML file. It doesn't store the entire contents of the file. It is an XML file. So based on the contents of whenever you load the XML file, based on the contents of that XML file, so actual data will be read from some other raster. So instead of saving the entire contents once again, you are just saving a virtual raster. So GDAL.autocreate warped VRT. So it takes these arguments, like have your source image and what is the projection on your source image. Similarly, then the third argument is to which projection you want to reproject your image. So anyway, we have created here a new projection. So that is but this takes an indent WKT format. So we are converting it to WKT format. And next argument is what method you want to use for interpolation. So we are using GDAL.bilinear, or suppose if you can change it to nearest neighbor or any other technique for so average bilinear cubic slice, whatever you want, nearest neighbor. If you want to change, you can change the interpolation scheme accordingly. So VRT DS, so it creates a virtual data set. So now suppose let us see that how the images look like. So old underscore ds dot read as array is our original image, and virtual ds dot read as array will be our reprojected image. So you can see that slightly the images, this is the original image, and this is the reprojected image to the UTM projection. So now let us read the projection information from our virtual data set. So VRTDS.get projection, then it says it's a UTM GeoGCS based on GeoGCS. So this is the way how do we reproject our image. So we can call auto create warped VRT. So that takes these 4-5 arguments. Your source data set, what is the projection on your source data set, then to which projection you want to reproject your image. Thus next argument is the interpolation technique what you want to use. So then even this VRTTS, that even you can save to the disk, like you can call VRTT or create copy method on this VRTTS, or directly you can use GDAL translate for writing it to the disk in TIFF format. Suppose if you don't want to make virtual raster, instead of that, then you can directly write a TIFF or any other image. So this way we can reproject our image. So next is mosaicing. Let's see how do we mosaic the images. So what is mosaicing? So mosaicing is a combination or merging of two or more images. So here we can see that suppose this we have these images whose so this image corresponds to this geospatial geolocation. Then this image on these are we have multiple images. Suppose now we want to combine these all images to a single image, so that our image looks like this. So that is called mosaicing. So mosaicing means combining spatially different, combining multiple images spatially. So we are combining the images based on their geolocation. So that is called mosaicing. So for mosaicing, what we will do first we have what we have to do. First we have to, suppose we have these multiple images. So first thing we need to calculate the extents of our mosaiced image. So what will be the extent of our mosaiced image? So for that we need to calculate what is the minimum extent of all these images. What is the leftmost extent the image is covering? Similarly, we have to calculate out of these images what will be the rightmost extent, then leftmost and topmost, then bottom and top. So this way, suppose these different colors images were there. So this will be the extent of this entire area. This will be the extent of our mosaiced image. So what will be the extent? Like we have to calculate the minimum minimum longitude of all the images, same way maximum longitude. So our mosaiced image will cover this minimum minimum longitude to maximum longitude. Similar way, latitude wise minimum to maximum. So our first job is to calculate the extents of our mosaic based on these sub images. Then next job will be like we have to calculate this. Once we calculate the extents of our mosaic image, so based on these sub images we will calculate the extents. Then we have to calculate this particular subset where it will fit on the mosaiced image. Suppose this image is going to fit on line number 5. Suppose it may be like this image might fit on line number 10 to 10 pixel number 10 to some other area. Then this particular image may fit on the line number 15 to line number 15. Another image may fit on line number 20 and so on. So first job is we have to calculate the extents of our mosaic based on the sub images. Then next job is to calculate where that sub image will fit into our mosaiced image. So those two things, if we are able to done, if we have done both those things, then what we can do, we can keep on reading one by one all our sub images. Then just copy those. Once we got that in the mosaiced image where this particular sub image will fit, then we can just copy that contents of that sub image to the specified location in our mosaiced image. So for anyway, calculating the extents is quite easy, because first we can calculate the extents of each of the individual sub image. Then we can find minimum, like we can calculate the minimum out of all the image, or like suppose we want to calculate what is the left extent of our image. So that will be the minimum of left longitude of these images. Similarly, maximum will be maximum longitude of all these images. Similar way, what will be the minimum latitude? So minimum latitude will be minimum latitude of all of these images, and maximum latitude will be maximum latitude of all these images. So calculating the extents of our mosaiced image is simpler. Then next we will calculate where this particular sub image will fit into the mosaiced image. So for that we will use another class available in GDAL, that is called a GDAL transformer. So with the help of GDAL transformer, we will translate our sub image. We will calculate the position of our sub image in the complete mosaiced image. So I will explain with Jidal transformer first. So what is Jidal transformer? Jidal transformer creates image to image transformer. Image to image transformer means, suppose we have this geo transformed image, and we want to calculate on the this particular image where this particular sub image will specially fit. So this so that is the that we will do with the help of Jidal transformer. So Jidal transformer, this function creates a transformation object that maps from pixel line coordinate on one image to pixel line coordinates on the another image. So with the help of Jidal transformer, we will transform like our sub image where will it fit into our mosaiced image. So actually, if all the images are all the images are in have the same projection system, then it's quite easy to calculate. But suppose all of our images have different projection system, then it's quite challenging thing to calculate those things. So for that we need to first reproject all the images to the same projection system, then we can calculate. So there is a instead of that we have a Jidal transformer that directly does this for us. So the Jidal transformer does the following things. So first, what it does at the first stage, from the source image line pixel coordinate to, so every image line we convert to georeference coordinates. Then second stage, it changes the projection from the source to destination coordinate. Then third stage, it converts destination image geotransparent coordinate to destination image coordinate. So with the help of this, finally it gives us the coordinates in image this destinations image coordinate system. So let us see with an example. Suppose now I will use the same file. So first I will open with calling jidal.open file. Now anyway, this is the projection system of our original data. Now first thing, we need to create a transformer object. So transformer object takes 3 arguments. If I see here, so first argument is source data set, then second argument is destination data set, then there are some keyword arguments that you can pass it in. Suppose now I am creating a Jidal.transformer. So source data set, I am passing what data set I have created. Then destination data set, suppose now anyway right now I don't have created the mosaic data set. So I am passing it as none. So when I pass the destination data set as none, it works. This Jidal transformer works as a once I explained that applied transform function. So in that case it works at applied transform function. So if the destination data set I have defined as none, so Jidal transform, what it will do, it will just calculate from our real world coordinate, if you know the real world coordinates of our pixels, then what Jidal transform will do, it will just give us the latitude and longitude of our that pixel. So suppose here I have, instead of, because right now I don't have any mosaic destination data set, so I am just passing it none. So if I now this is created a transformer. Now for that, now suppose if you want to convert from one image coordinate to another image coordinate, so we need to call a function called transform point. So transform point will convert pixel coordinates from line number and pixel numbers from one image to another image. So transform point, actually first argument is so destination to source flag. So this destination to source flag says that if you want to compute the offset from destination raster to source or vice versa. So this particular transformer you can use for either way. Suppose if you want to compute the offset from destination to source, then you need to pass it false, and if you want to calculate from source to destination, then you need to pass it as true. Suppose now anyway our destination data set we have set as none, so transform dot transform point and false and 0 0. Suppose if I give it 0 zeros initially, so this gives the coordinates corresponding to pixel number 0 and 0. So 82.9 and 31. So similar way, suppose 10 10 for pixel number, this will give the coordinates for pixel number 10 and 10. And suppose instead of this, if you call transform dot transform point with argument as true, so what this time it will this will take these as coordinates and try and will give us the pixel line number and pixel number in our image. So anyway, see our image starts at so as you can see that our image starts from 82 and 31. So suppose if we give the coordinate at 10 by 10, so it is giving the line number in negative. So anyway, these things doesn't exist on our image. So suppose if we want to convert for 82.99 and and 31, then it should give 0 zeros. So it's almost 0 zeros. So this way we can use Jidal transform for converting both ways. I suppose if you want to convert from real world coordinate to the image coordinate, like from latitude longitude to the line number and pixel number, or from line number pixel numbers to the coordinate. So both way it can be used, transform point it can be used. So now let us use it in a real scenario where I will mosaic multiple images together. So here in my mosaic folder, I have mosaic folder. Here I have 4 images which are, so we will combine these 4. I will create a mosaic from these images using Jidal transform. First I am changing my working directory to this directory. So these are the files which I have. So these are all bound to rasters. So first I have defined the file names. So first thing what we need to do, first we need to calculate the extents of all of our sub images. So for that what we have written, I have just written a function like calculate extents. So calculate extents will take our, first we will open the file for reading. So that will return us a data set. So from the data set we can calculate the extents of any of our image. So first thing we are getting the geo transform of our image. Then as we know that geo transform has 6 elements. So left extent are creating by 0th element of the same extent. Then rightmost extents we can calculate by using this. Then this way we will get the 4 extents, left, right, bottom and top of our image. So this calculate extent function will give the extents of our image, leftmost longitude, rightmost longitude, bottommost latitude, and so like this is min x, max x, min y and min x, max x, min y and max y. So this function will give the 4 extents of our image. So this function we will use later on. So first thing here, now I am creating a data set list. So in the data set list we will read all the images one by one and store those data sets in our list, and these are the extents. So every image we will read and store the extents of each image in a list. So what this calculate extent function is giving the 4 extents of our image, left, right, top and bottom. So here first, anyway, this is rudimentary. So first we are doing I will examine the file names variable. File names contains the names of all my files which I want to mosaic. These are the 4 files which I want to mosaic. So what I am doing first in file names, I am opening the file for reading. So first time this particular file will be opened for reading. So DSS equal to zidal.open this particular file. Then we are calling extent, calculate extent. Then we are calculating the extents of this particular raster. So what will be the extent? These extents will be calculated using these functions. So extents are nothing, just leftmost latitude, then how much area that particular raster is covering. So from this longitude range to this longitude and this latitude to that latitude. So we are calculating the 4 extents of this particular image. Then I am just putting these extents I am pushing into some another extent. I have created a list in that I am putting in, so that later on we can calculate minimum extent, minimum and maximum from this list. Then these data sets also we are just appending to a list. So we are reading one by one the file, then calculating the extents of this file and storing the extents of this individual file to a list. And similar with that data set also we are storing to another list. So now if you see what extents contain. So extents contains now 4 items. So first is the extents of first image. So our first image has the minimum latitude 77.9 to 78.25, 29.99, 32, 30. Similar with these are the extent of second image. This is the extent of third image. This is the extent of fourth image. Now with the help of these extents we can calculate the extent of our entire mosaic. So what will be the extent of our entire mosaic? So that will be like minimum extent will be the minimum out of these. So minimum out of these leftmost will be our extent of our mosaic image. Similar way, what maximum longitude? So that will be the maximum of these rightmost corners. The similar way, what will be the bottommost? Bottommost will be minimum of all these 4 mosaics. Similar way, maximum latitude will be maximum of all these mosaics. So this way we can calculate that what will be the extents of our mosaic image. So now for finding minimum maximum we are just converting this list to a numpy array using np.array function. So now if I convert it to numpy array, now if I see the numpy, now it has become a 2-dimensional array. So it is very easy to calculate minimum and maximum from this 2-dimensional array. Thus I can call a np.min function. So mosaic left. So what is the leftmost extent of our mosaic image? So that will be the minimum of this column, because this column contains the left extent of all our images. So minimum of all those 4 images will be the extent of our mosaic image. So just I am calculating np.min from this column, all rows and zeros column. Actually just I can write zeros column. So this way, with this I will calculate the left, similar way right, top and bottom. So if I see this, so this way we can calculate so what we are doing here, these are the longitude what our image will cover. So how we are calculating, so out of this, from this minimum we are getting, so minimum from this will give us the leftmost extent of our image. Similar way from these 2 columns if you get the maximum, so that will be the maximum, the right extent of our image. Similar way, minimum of these things will be give us the bottom extent, and max of these latitude values will give us the top extent of our image. So this way we have calculated the extents of our mosaiced image. So our these are the extents of our mosaiced images. It will cover 77.99 to 78.50 and 29.74 to 30.25. So this will be the extents. This will be the extents of our image. So here just we are copying the getting the projection information. Actually now DSS variable will contain the projection from the last image. So now here we are assuming that all of our image has same projection system, same same projection and same spatial resolution, but later on you can implement it such a way that you can handle different projections, different resolution as well. But for the simple case, so I'm just copying the projection and transformation information from one of my rasters. Then just I am copying the transformation information from one of our raster. So in the new mosaic image, actually only the extents will change, but the spatial resolution remains same, because we are assuming here that the resolution of all of our images is same. So I am just copying the projection transformation information from one of the image. So if I see this, so this is the transformation information from the last of the image. So here we can see these are the coordinates of x0 and y0, 78.24 and 30.00, and this is the resolution. Now our mosaic image extends x0 and y0 will be the new value. So that we are doing here on the mosaic transform. I am assigning the new values whatever we have calculated. So TRF0 I am assigning the left, and TRF3 corresponds to Y0. Y0 I am assigning whatever we have calculated the rightmost extent of our top extent of our image. So now if you see the mosaic transform, so this is the transform of our new mosaic image. So now this is the x0, and anyway the resolution remains same. Then north is up, so it is 0, and then y0 is 30.25. In the last image was 30.0. So this way we have calculated the extents of our mosaic image. Now first we need to create a data set. So similar way, like first we are calling GDAL dot, suppose if you want to create a geotiff, GDAL dot get driver name by geotiff. Then first what we need to know the width and height. So how many pixels width and height of our mosaic image. So how do we calculate the width and height of our mosaic image? Anyway, we know the rightmost extents and leftmost extents. Similarly, we know the bottommost and topmost extents. So if we divide that extents using spatial resolution in the x direction and y direction, we will get what will be the width and what will be the height of our image. So same thing has been done here. So mosaic right minus left, and it divided by the spatial resolution in x direction. Similarly, right, bottom minus top, because we want y in negative direction. So bottom minus top divided by the resolution in y direction. So that will give the height and width of our mosaic image. So this is bot. So this way we have calculated the width and height. So if I see, so 2263 by 2263 will be the width and height of our mosaic raster. So now anyway we have calculated the width, height. Now just we will, on the driver we will call create method. So we will call that out ds or destination ds, anything you can call. So driver dot create. So driver dot create, then we want to give it a name mosaic underscore list dot if. Then we have to pass it the width, and we have to height, that whatever we have calculated, and data type. So data type, in the original images the data type is unsigned 16-bit integer, so we are just passing that. Then we are setting the copying the projection and transformation. So out underscore ds dot set projection, that projection information we are setting as one of the source images. So that anyway we have calculated, we have copied in the projects variable, and we have, and here you can see that we have calculated new transformation information for our image, so that we are setting. So once this is set, then our destination data set is ready. Now what we need to do, we need to, now we will read one by one our sub images. We will read one by one the sub images in our image, and what we will do with the help of transformer. With the help of our transformer, we will calculate the pixel number, pixel number and line number in the mosaic image where that sub image will fit. So here you can see that for DS in DS list. So DS list contains the data, all data. In DS list we have stored all our images which we wanted to mosaic. So now we are looping over one by one over that DS list. So first thing we are creating a transformer object. So GDAL dot transformer. So here our source is our sub image, and destination is our mosaic image. So mosaic data set is this. Anyway, we have calculated the width and height of mosaic. We have set it projection, transformation information. So now we are creating a transformer object. So transformer GDAL dot transformer. So our source is our sub image and destination is our mosaic image, because now we want to calculate first where this our sub image will fit in the mosaic raster, like in which pixel number and line number this particular subset will fit in our mosaic image. So for that, for calculating that, first we have created transformer object. Then on the transformer object we are calling the function transform point. So this transformer dot transform point. First argument source destination. First argument we have passed as false. This I said, if we have to calculate from source to destination, if we have to calculate from source to destination, that we need to pass it as false, and like for which location you want to calculate. So this this will give, that this will tell that our source images, so destination data sets 0 point where it will fit in the mosaic data set. So this will give whether success or false. So if it's X, you see this returns two values. One is success. So if it has returned 0 means successfully it could transform the point, and second it returns XYZ, like pixel number, line number in or destination data set, so where that will fit. So suppose first I will show you the simple example, then we will loop over. So suppose so first we have created a transformer object GDAL dot transformer. This is our source image, is our sub image DS. Over here now it will be DS list 0. So for 0th first image I am calculating. So now if I see XYZ, So it says that this particular image will fit at these locations. So these are zero zeros. So this is says that this sub image will fit at this location in our mosaic raster. So this way we are looping all over the all over the images one by one, and just we are calculating that offset to an integer value. So this will return three values x, y and z. So anyway we are interested just in x and y. So this way we got the the pixel number and line number of our sub image in our mosaic image. So finally, so this will be like our now we are reading the data from our sub image. So ds dot get raster band 1. So anyway our images are single band image, so we are just reading one band. So that data we got data. Then this data we will copy it into the destination data set. So our out underscore ds dot get raster band 1 there dot write array. So there we are copying the data from our source image starting from this location. Anyway, this in the destination we have calculated that this particular sub image will fit at this x and y, this line number and this pixel number. So we are just copying the data from source image and copying and pasting it to our destination data set. So this has copied all our data. So here what is happening, if two sub images are overlapping, the data from the last image will just we are just overwriting. So later on what you can do after this, like overlapping areas you can calculate, and there you can calculate mean, max or some any other function you can implement. Here by default what it is doing is we are just copying. So here what will happen, the image which will come in the last in the loop, so that data will be just overwritten in the overlapped area. So now suppose initially let us see the images one by one, how the original images were there. So these were our original images. So these four images now we have mosaic together in a out underscore ds. So let us visualize. So mosaic data is our out underscore ds dot read as array. So that we have written everything. Now we can read the data. Now let us see this. So this is our mosaic image. Here you can see that these four especially different images we have combined into a single mosaic. So this way we can come. Then later on, suppose this your image is very big, then suppose if you want to attach overviews or overviews with your image, so that also can be called using out underscore ds dot build overviews. Then you want to calculate the average of those pixels. You want to average for interpolation. So 2, 4, 8, 16 and 32. What does it mean? That now pixel size will double. So suppose initially pixel resolution was 1 meter, then first overview will build as 2 meter, then 8 meter, 16 meter and so on. So this way these multiple overviews will be created with the image, and finally we have to flush and delete. So this way we can mosaic images together. So mosaicing images is quite simpler operation. So first thing what we did, we based on the sub images we calculated what should be the extents of our mosaic image. So we calculated the extents of our mosaic image. Then we based on the resolution we calculated how many rows and columns will be there in the mosaic image. Then our next job was we calculated where this sub image will fit in the mosaic image. So that we did with the help of a transformer function. So once we got the pixel number and line number of sub image in the mosaic image, then we just copied the data. We read the data from our sub image and pasted in the line number and pixel number in the mosaic image, and that's all. So this way we can create mosaic. So next is local analysis. Now let us see that how do we do some local analysis on image. So what local analysis means? Local analysis work on two images or arrays that are of the same shape and same size, like they are the same shape. So an algebraic equation we can apply to each location, apply each set of locations. Like one common example, One common task in multispectral imagery is to compute like various indices. Suppose if you want to calculate NDVI or NDWI, so something. So what do we do? The algebraic equation is applied to every pixel. So that we will call local operation. Like here you can see that these are the two images, and we have just added those images pixel by pixel. So every pixel, so on every pixel we have applied some operation. So that is called local operation. So this is a simple example like NDVI. NDVI, what do we do? We calculate the normalized difference of a red and NIR band, and we see that. So with that we identify the vegetation. So the for pixel which has NDVI greater than some threshold like maybe 0.3, 0.4. So those are vegetations. So that way we can find vegetations on our image automatically. So this is called local operation, where we apply some algebraic operation on two images of the same size pixel wise. So on every pixel we will apply the same operation. So like here we are adding two pixels together, we may subtract, divide, or we may apply some, we may get some normalized difference between two bands and so on. So let us see how do we calculate this. So what is NDVI? So NDVI is normalized difference vegetation index. So this is a simple index that uses red and near infrared wavelengths to produce a number so in range -1 to 1. So growing plants use red wavelength for photosynthesis, but they reflect near infrared radiation. So high ratio on these numbers indicate that there is a healthy vegetation. So with that, suppose if we have calculated NDVI using the formula NIR minus red divided by NIR plus red, then the pixels which are showing values above certain threshold will be a healthy vegetation. So now here we will see that how do we calculate NDVI on one image. So either you can, suppose here we have images, different bands are saved in different images. There may be a case that when you have a stacked image, so either you can do these operations on a stacked image, multi-band stacked image, or on different images as well. So here I have images which different bands are stored in different different files. So here I have my data in this file. So here my NIR image is stored in band 4 is NIR and band 3 is red. So I have just created the variables with these names. Okay. Now one by one we will first start reading the file. So red data set is equal to, we are just opening the file. So red band we created. So red ds will be gdal.open. Similar way NIR, we have opened NIR image. Now once we have opened the image, we get a data set. Now we will extract the data, because finally we have to do some calculation on the pixel values. So red band data we are calling a red data set dot get raster band 1, and we are just inquiring what is the data type available with this band. So it says unsigned integers, unsigned 16-bit integer. Similar way NIR we have got, we web fetch the NIR band from our NIR image. Now actually if you see here, the data type of both red and NIR is unsigned integer 16. So these are unsigned integers. So this will take only positive values. So suppose if you will try to do subtract operations, so that will not be proper here, because suppose because these two are unsigned integers, then the resulting number also will be unsigned integer. So it will not be a correct thing. So whenever the result like NIR minus red will come in negative, so unsigned integer because unsigned integer can hold only positive integers, so you will get the wrong result. So what we need to do, first we are converting these unsigned numbers to signed numbers, so that our subtraction operation will be fine, because otherwise because negative numbers cannot be represented in the unsigned format. So if you just do red minus NIR there, for negative numbers you will get very high value. So before applying negative operation, minus operation on unsigned integers, we need to convert them into signed numbers. So that anyway, these all will be positive numbers. So even if you convert to signed numbers will remain same only, but only thing difference will come when we apply minus operation. So if you apply any minus operation on unsigned integers, so we will get positive number only, but negative number converted to positive. So for that we need to first convert them to signed integers. So for that, what we are doing for now, red band we have fetched red band dot read as array, and we are converting from unsigned to signed 32-bit integers. Because if we convert unsigned 16 to unsigned 16 to signed 16, only the numbers interpretation will change totally. So we are from 16-bit we are converting to 32-bit, so that the sign bit remains same only. So as type, so first we are converting into signed number. So red will be, let's suppose if your original image itself the data is available in the signed format, then you need not do this step, convert it to the 32-bit. But as this, in this case our data type is unsigned 16-bit, so we have to apply a minus operation, we are converting it to the signed 32-bit. So once we got the red and NIR values, so next we can apply directly the formula, because red and NIR, these will be two-dimensional numpy arrays. So on the numpy arrays we can apply the formula like, so NDVI equal to, so NIR minus red divided by NIR plus red. So just so simply, just you can write NIR plus red. Now suppose see the result. So if you see the result, now you can see that the areas which are shown in bright color, so this is vegetation. So this way you can find very easily, you can calculate NDVI, and you can see that the areas which are seen in bright portion, this all is vegetation. Similar way we can calculate NDWI. NDWI is normalized difference water index. So suppose if you want to automatically find the water bodies in your image, so that you can make the, visually you can find, but suppose if you want to find out through your program, you want to find out water bodies in your image and make a map from that. So let us see that how do we calculate NDWI. So NDWI also is similar thing only. NDWI formula is green band minus NIR divided by green plus NIR. So here my image is green and NIR images, anyway NIR image range same only. So NIR image and green image is band 2. So these are my two variables. Then similar thing, now here I have combined two steps together. So Jidar, first I am opening the green image, then just reading the from the data set, then converting it to signed 32-bit. Similar way for NIR also, open, read as array and convert it to signed 32-bit. Then later on, then next is the formula. So NDWI equal to green minus NIR divided by green plus NIR. So this way we calculated NDWI. Now suppose if you want to visualize, now you can see that all the pixels which are water, they have become brighter. They have become brighter. Now suppose this image contains all the pixels. Now suppose if you want to mask all non-water pixels, so that we can do with the help of numpy array very easily. As I explained in my last lecture, either we can use masked array or we can use np.var with the help of np.var function. So anyway, here we can see that. So we can, all the pixels which have the value above 0.2 appear to be water pixels. So we can apply np.var. So anyway, here we have NDWI variable which holds pixel values. Now suppose if I try it here, NDWI equal to np.var, wherever and in whichever pixels NDWI is greater than 0.1. So those pixels I want to retain as it is, or I just can assign them the value 1, and all other pixels to be 0. So what I am doing here, we are masking all the pixel which has value less than 0.1. So this way we can just keep the pixels only water pixels and mask all other pixels. So if you see here, now you can see that only all other pixels have become 0 and the pixel on the water pixels have value 1. Or suppose if you can, otherwise you can, if you want to use masked array, or you can use masking also. So suppose if you want, so I will say water mask masked less than 0.1. So I want to mask all the pixel which has value less than 0.1. So in my original array is ndwi 2.1. So now instead of this I will just print water mask. So here you can see that we have, out of our image we have extracted only water pixels. So this way even if you want to visualize, so either you can use np.where or you can use masked array. So this way you can run this analysis on any image and so on. So this way we can extract, so ndvi, ndwi or any other image or any other index. So this way you can mask those pixels, extract those values and do some analysis on your image. So finally after this is done, then there is called global analysis. So in the local analysis what we have done, we have applied some operation on every individual pixel. Now there is another thing called global analysis. So global functions work on the entire image, such as proximity that will run on entire image. So global analysis we will do, such as suppose if you want to do proximity analysis or cost distance analysis. So a proximity analysis, maybe suppose you have an raster containing the roads. Now suppose if you want to calculate the distance or distance of every pixel from the nearest road. So that you want to calculate that which areas will be developed. So the areas which are nearest to the road will have the higher potential of development. So this way global analysis, or we call proximity analysis. So in proximity analysis what we can do, we can calculate the distance of every pixel on our image to the nearest pixels which is road. So in this way we can calculate the, suppose now here what we will do, we have a water layer. So in water layer we have like this water, we have a water map like this, and we want to calculate the distance of every pixel to the nearest water pixel. So this way suppose we want to create a proximity map for this much area, and what we want to do, we want to calculate the distance of each pixel. So we want to create a proximity map, distance of each pixel to the nearest water body, nearest pixel which is classified as, so this particular pixel, how far it is from the how far it is from the nearest water pixel. So suppose this type of proximity map we want, we can do that analysis using JDAL has a tool called proximity analysis tool. So with that we can do the proximity analysis. So here I have a water layer like whatever we generated here. So I am just opening the file. Then I am fetching a band from that water. The image is not available right now. I'll just copy the image. So this is my water layer. So I have just fetched a raster band and I'm just reading the data. And actually this data has like pixels we have classified in three classes, 1, 2, 3. So what I want to do, all pixels which have greater than 1, I am just assigning 1 and remaining to 0. So here we are masking all other pixels. So suppose if we see, so this is our image. So in this image, all the pixels, all the water pixels are 1 and other pixels are 0. So now what our job is, we want to we want to create a proximity map for each of these pixels. So in this entire area, we want to calculate the distance of each pixel to the nearest water pixel. So that we'll do using Jidal proximity tool. So first thing what we need to do, first we need to create a similar raster of the same shape, size and transformation as our source data set. So what I am doing, I am calculating the width and height of my original data shape. Then we are just creating a driver, and on the driver, with the driver we are creating a data set. So a data set, this particular data set will have the same dimension as our water layer, because on the same thing we want to calculate, like we want to create the proximity map for the all the pixels in this data set. So the distance of the distance of all these pixels, distance of to the nearest water pixel. So here I have just created a destination data set, and I am setting the projection and transformation of this to same as our original image. Now this is the function that we'll use for calculating proximity. So Jidal dot compute proximity. So this function calculates the proximity. So Jidal dot compute proximity. First thing is the band. First thing the source image, source band, right? For which band you want to calculate the proximity. Then the resulting operation, where do you want to save? So this will be our destination. So band is our original water layer, and destination is we have created a proximity dot tiff. So we want to save the results in destination. So what this proximity function will do, this for these every pixels calculate the distance from nearest water pixel. So because we are calculating the similar proximity map, so this proximity map will be same as this size and transformation, projection, everything will be same as our original image. So band and our destination data set, we are getting the first raster element. Then the next argument is distance unit, like this distance you want to calculate in geo or pixel number of pixels. So how many pixels, this distance you want to calculate in pixels or distance. So here you can pass geo. Suppose if you want to calculate in terms of meters or kilometers, otherwise you can pass in number of pixels. So if you see this has created a proximity map, and now if you plotted these together, so this is our proximity map. Where you can see that in these areas the pixels with bright value means more distance. So here you can see that this is the image. In these areas the distance, these pixels are near 0, and these are the brighter pixels. These are the pixels which have more distance from the nearest water pixel. So this way we can do proximity analysis on our image. So then finally we have done, and you can save it. Next is DEM processing. Suppose now you have a digital elevation model. From that you want to calculate slope, aspect, hillside, or anything from for your image. So that also can be done using GDAL. So like suppose here in an example I will see that how do we generate a hillside from a DEM. So hillshade obtains a hypothetical illumination of surface by determining illumination values of each cell in a raster. So it does this by setting a position. So it assumes that if there is a hypothetical light source and calculates the illumination values of for each cells in relation to its neighboring cells. So this will greatly enhance the visualization of a surface for analysis or a geographical or graphical display. Suppose when you are using some terrain analysis if you want to do so, there the hill shading helps. So here we have a dam. So for creating a hillshade, we need to call gidal.dem processing. So gidal.dem processing. Then first argument to it, the destination raster where we want to save our hillshaded image. Then next is our source image. Then third argument is processing. Actually, what processing you want to, whether you want to calculate slope, aspect, hillshade, or anything else, or similarly format, in which format you want to. This is an extra argument. So you can pass this way. So this will create a hillshade. So now it has created a hill.tif. Now suppose if you open and see the hill.tif image, so it has created an image like this. For our dam, it has created a hill shaded image. So this way we can do some sort of analysis automatically, slope, aspect, or anything on our dam. So that's all. Thank you much for today.